So we just finished talking about oxidation reactions. So the two biggest reactions we talked about today were dehydration reactions of alcohols, and you form an alkene, form a double bond, and then oxidation reactions. Okay. And that's different. What you get, your product is different depending on if you have a primary alcohol that's being oxidized, secondary alcohol, or tertiary alcohol. So let's put this into practice, what we just did a few minutes ago. From what alcohols might the following products have been made? From what alcohols? So we're working in reverse here. We're taking the product and we're backtracking. We're saying, okay, instead of oxidizing, what if we reduce it back to the alcohol that we originally should have had? What would we get? Well, what we have here, you got to look at you got to be able to identify what you have. What kind of product did we get here? Is this, remember, by the way, tertiary alcohols don't react. So none of this, we're not going to form tertiary alcohols. We're going to be making secondary or primary alcohols. So what kind of product is this? If you look at this, what kind of functional group is this? On number one. Basically, you just say, okay, is it an aldehyde, a carboxylic acid, or a ketone? Somebody.
Is it a ketone?
It is a ketone. How do I know it's a ketone? Because we have the carbonyl carbon right here, double bond the oxygen, and we have two carbon groups bonded on either side. Okay, that's a ketone. So remember, what kind of alcohol produces a ketone when it's oxidized? That is a secondary alcohol. Okay. So basically all we're going to do, let me erase and you can see clearly here. We're going to form something just like this. And these R groups, guess what? These R groups are going to be these two methyl groups. So the alcohol should look like this. We're going to throw a hydrogen on here, and we're going to put a hydrogen on right here. And this is going to become a single bond. We're going to undo the double bond. The double bond's formed when we oxidize it. So if we're doing the opposite, we're reducing it, we're going to take it back to a single bond. So this should look like this. Now it's an alcohol. And that is a secondary alcohol, right? Okay, number two here. What kind of product do we have? Again, you need to ask yourself, is this an aldehyde? Is it a ketone? Is it a carboxylic acid? So let me remind you, aldehydes, some kind of carbon group, we'll call R. Then you have a carbon double bonded oxygen with a hydrogen. That's an aldehyde. Carboxylic acid, some kind of carbon group, and here's your carbonyl carbon, and you have an OH. That's a carboxylic acid. I'm going to abbreviate. Ketone, you have some kind of R group, which is a carbon group. Then you have your carbonyl carbon and another kind of carbon group. That's a ketone. Okay, so these R's are both carbons. All right, so what do you think number two is? Is it aldehyde? Is it a carboxylic acid? Or is it a ketone?
Hey, Dr. Eller.
Yeah, right.
I just want to let you know I'm with Cassidy. My internet connection keeps saying it's unstable and it keeps going on and off, but I'm here.
That's what I see you on both. Okay, that's totally fine. Whatever you got to do.
Okay, thank you.
What do y'all think two is? So here's our carbonyl carbon. Here's what I see. I got a carbon group here and a carbon group there. So what is this?
A ketone.
Thank you, Cameron. So just like number one, when we reduce this, it's going to be reduced to a secondary alcohol. So we're gonna throw a hydrogen on right here. This O is gonna become the OH group. That's the alcohol. That's what makes it alcohol. And we're gonna put the hydrogen back on the carbon, the carbonyl carbon. And then this double bond becomes a single bond. That's what happens when you reduce the ketone here. So our product will be, I'm gonna redraw. Okay, this is a cyclic 7 carbon structure. These are the hardest for me to draw. I hate drawing cyclic structures with 7 carbons, but we can do it. Made that way too long. I think that's 7 carbons. And then this becomes an OH. Okay, now if you, again, y'all are always like, I want to draw the hydrogens in. If that helps you, draw it in. I prefer you not. But if that helps you see, okay, one hydrogen was added on here, the other hydrogen was added on here, now we have a single bond, secondary alcohol. So what we're doing here is we are reducing carbonyl compounds to the respective alcohols. We're doing the opposite of what we talked about with all the oxidation. I know this is oxidation reactions, but it's a continuation of what we we're talking about up here. Okay, so here's our product. You got to ask yourself, what functional group do I have? Is this a ketone, an aldehyde, or a carboxylic acid? Zoom in on the carbon-oxygen double bond. Okay, and then look at what is next to that. This right here is what we call the R group. This is R. Okay, we don't care about that. To identify it as a ketone, a carboxylic acid, or an aldehyde, we are just looking at this part. So which one of these up here does that correspond to?
Carboxylic acid.
Yep, carboxylic acid. So remember, let's go back up here. When you have a primary alcohol, on highlighter, when you have a primary alcohol and you strongly oxidize it, you get carboxylic acid. So we're going to reduce this, that you don't have to draw the aldehyde intermediate. Okay, that's kind of the intermediate step. You don't have to draw that. You can just go all the way back to a primary alcohol. Okay, so what that's going to look like, we're going to put the one hydrogen back on here. This OH group is going to leave, and in place of it, we're going to bond a hydrogen. And again, always the single bond or the double bond becomes a single bond. So let's draw that out. We got CH3, CH, none of this part of the molecule has changed. And then CH2, and then C, we said we're going to put a hydrogen on that. And then that's going to be bonded to the OH group, single bond. And this is a primary alcohol. Why primary? Because this carbon right here, the one that's bonded to the hydroxy group, is only bonded to one other carbon. That's what makes it primary. Okay. All right. Questions on that? This was not an easy task. So if you're like, ooh, I need to practice that, that's okay. I don't consider this to be one of the easier things. Okay, any questions? That's it for alcohols. That's all we're going to talk about with alcohols. So the major types of reactions, again, are dehydration reactions and then the oxidation reactions. Okay, and then you know the properties, like where they would have higher or lower boiling points than alkanes or ethers. Now we're going to talk about phenols a little bit. Okay, phenols are very useful. Okay, phenols are especially useful all of 2020 because why? They're the primary things in a lot of disinfectants and antiseptics. What's the difference between a disinfectant and an antiseptic just from looking at these pictures?
Disinfectant is a spray and antiseptic is more of a gel.
Okay, not quite, Madison. The point there, yes, that's what the picture show. Disinfectants are used on surfaces. Okay, you're cleaning surfaces. Antiseptics are for biological purposes. Okay, they're used on humans. We're not going to use a disinfectant on a human. You can use an antiseptic, but not a disinfectant. Okay, I know the words sound really similar. Disinfectants are for cleaning surfaces. Antiseptics are for cleaning skin or things like that. You can have liquid antiseptics for sure. Like post-surgery, a lot of times you got an open wound and you got to make sure that thing is completely sterilized. They'll use antiseptics to clean the wound area or the surgical area. Okay, properties of phenols. They're more water soluble, higher melting, higher boiling points. Why? Because phenols are highly, highly stable. They have that aromatic compound, and aromatics, remember, they don't react with anything because they're so stable. So that's going to lead to higher melting and boiling points. Then similarly substituted alkyl benzenes, okay? So an alkyl benzene, what is that? An alkyl benzene might be like this. And then you got it's an aromatic, and maybe it has a CH3 group branched off, but a phenol, we know, is this. Got the double bonds, and we got the OH group. Why does it have higher melting points and boiling points? Because this can hydrogen bond. Okay, that substituent, the OH constituent, that can hydrogen bond. This cannot hydrogen bond. So this is all nonpolar, and this part is polar. Okay, therefore it can hydrogen bond, leads to higher melting points and boiling points. All right. So as we just said, phenols can hydrogen bond. Compared to alcohols, phenols are less water soluble. Okay, because you have that huge hydrocarbon ring. Okay, and that is hydrophobic. Okay, so they're really way less soluble than alcohols. That's what we just said. Benzene ring is very hydrophobic. Okay, but they're more acidic than alcohols. Why? What does that mean? Well, here's why they're more acidic. This hydrogen is readily pulled off. Okay, an acid is something that donates a hydrogen. So this hydrogen it readily leaves because this ring is so stable. And it can handle any charge discrepancies that's left on that oxygen. So the oxygen will be left with a negative charge. That's okay, the ring can handle it because it's so stable. And that's what makes it even more acidic than regular alcohols, okay? All right, naming phenols. So compounds with phenols are named, you just put phenol at the end. So for example, it actually is quite easy. We've already learned how to name aromatics. We spent some time yesterday doing that. So if we have, remember the numbering 1, 2 is ortho. Okay, we talked about ortho meta para. So we've got a chlorine and a phenol. So this is going to be orthochlorophenol, or you could say O or 2-chlorophenol. So instead of just saying like benzene at the end, like we did yesterday, we're just naming it with a phenol ending. And we did some of that yesterday. Phenol is a particular kind of benzene ring. It's just a benzene with an OH group. So I want you to name these down here. What about this one on the left? We've got this is an iodo group. This is a methyl group. And then here is your phenol. So we're not actually going to use the ortho meta para here because we have more than 2 substituents. We got an OH substituent, we got a methyl, and we got an iodo. Now the OH is going to be named within the phenol parent name. So how would we name this? We know we're going to consider this to be carbon 1.
Since it's in a ring, we wouldn't say that it's 1 though. We just say phenol.
Right, you would just say phenol. You omit the 1. So look at alphabetically, iodo has to go first, and that's on carbon 3. So it should be 3 iodo, and then what? Y'all finish it for me.
2-methyl phenol.
Yes. No dashes between methyl and phenol. It's just one word. 3-iodo 2-methyl phenol. Okay, what about What about this next one?
Would it be, I'm not sure if I'm gonna do this right, but would it be 2,4-bromo phenol?
Missing one little part. Oh. What are you missing?
The double bonds, I need to like say where that's at.
No, 2, 4, you got 2 bromos, so we need a prefix.
Oh, dibromo.
Thank you, Abby. Yep. Dibromophenol. Okay, and that's it for phenols. Now we're going to talk about ethers and sulfides, and then lastly stereochemistry, and that's it for today. Oh, that's a lot for today. Okay, ethers. Remember, it's a carbon, oxygen, carbon group. And we're using R's there to indicate some kind of alkyl carbon group. It's not necessarily a methyl group. It could be a really long extended carbon group. So they contain 2 organic groups bonded to the same carbon. Okay, and it could be 2 different groups. I have these pictures over here. What are these pictures make you think of? Anybody ever had to have surgery done before?
Is
Anybody
it
been
an
knocked
epidural?
out? Do what?
Is it an epidural? The one with
One
the
is an
side
epidural. This is a picture of an epidural. Praise God for
and then
epidurals.
anesthesia?
And then anesthesia. Yeah, so an epidural is a kind of anesthetic, all right? So analgesics or anesthetics, we know these are used widely in health science world, especially if you're gonna be a nurse one day. And ethers used to be, they're not anymore, but kind of when anesthetics became a thing and people realized you could use certain compounds to knock people out while you do surgical procedures, ethers, the kinds of compounds they used for those anesthetics were ethers. Now, there are really hard side effects with those, so we don't use. This table shows you a summary. I'm not going to go through this table, but there's several compounds in here that are ethers if you look closely, okay? Now, again, we don't use these anymore. We have better molecules for that. Anybody ever heard of fentanyl? Okay. The only reason I had ever heard of fentanyl is because in the negative sense, okay, in the drug world sense, people are aware of fentanyl, but fentanyl is actually used as an anesthetic or an analgesic. Okay, it's got really powerful, it's really potent. Okay, that's why it's a very dangerous drug. But fentanyl is not an ether. We have much more better compounds that are not ethers used as anesthetics now, but they used to be very purposeful for this. So how do we name ethers? Identify the 2 organic groups, and then you add the word ether. So if I'm looking at each side of this one right here, I've got methyl and methyl. So guess what? This is dimethyl ether. No numbers, no nothing here. We're just naming both sides to the both alkyl groups. They both happen to be methyl groups, and dimethyl ether. Okay, and you're gonna do it alphabetically. So this, for the next one, this is ethyl, and this is methyl. So this is going to be ethyl, methyl, ether. That's fun to say really fast. Ethyl, methyl, ether. Cyclic ethers are usually named with common names, so we're really not going to get into that whole lot. We do have one aromatic down here, and we'll name that in a second. But we need one more rule before we can actually name that, because a lot of times what you see is ethers are a part of another kind of molecule. And we will name the molecule according to its parent name that may have a different functional group. And then we'll account for the ether as like a tagged on substituent, okay? So we often don't name ether molecules as an ether. We name them as another kind of molecule, and then we tag on the fact that the ether is somehow branched on as a substituent. So for example, ethers present within a compound containing other functional groups, we acknowledge them as a group. We call them an alkoxy group. Okay, so for example, what does that mean? If you have an OCH3 bonded to the rest of your molecule and it makes it an ether, we call it a methoxy group. There's a methyl group and there's an oxygen So we combine the words. Instead of a methyl group or an oxygen group, we call it a methoxy group. And it tells us there's methyl and oxygen in this branched group. Same thing if we have like an OCH2CH3. There's 2 carbons there, so we have an ethyl group, but we have an oxygen with it. So we call it an ethoxy group, okay? So how does this work if we're like naming a full compound? It looks very complicated. So if we're gonna name this, how the heck, we got an oxygen, right, or a hydroxyl group. So this is an alcohol, but we have an ether right here in the middle of it. How do we name this? So what these rules are saying is we're gonna name this as an alcohol, and we're gonna consider let me erase. We're gonna consider this right here as a branched substituent. We're gonna consider this as an ethoxy substituent. So if we ignore the ethoxy for a minute, how do we name this? We're just trying to name this right now. This is the first molecule we looked at today. Ethanol, right? It's an alcohol. 2 carbons. With alcohol, it's ethanol. Okay, so this is going to be this we're calling this an ethoxy group. And guess what? It is attached. That's not what I wanted. It is attached at carbon 2. All right, we're calling this carbon 1, carbon 2 of ethanol. So it is 2 ethoxy ethanol. And this is where my mind is just like, oh my gosh, are you kidding me? With organic chemistry. Keeping in line with the same type of thinking, look what we have. We have a phenol, so we're going to name it as a phenol. But it's also an ether because we have this carbon, oxygen, carbon bond. And that part is an ether. So how do we acknowledge the fact that there's this ether substituent? We acknowledge it as a methoxy substituent. So we'll say, this is going to be carbon 1. We always name the OH, the alcohol, as carbon 1, then carbon 2, and then this is carbon 3. So you can use the ortho-meta para here. This is going to be meta spacing or patterning. So you could say 3-methoxyphenol. Or you can say M for meta. Okay. This is our methoxy group. Okay, lastly, this one made me think for a second. We have 2 methoxy groups. We have 2 ether groups. So we're actually going to name this. You know how we name this? This is nuts. We name it as an alkane. I want you to name this middle portion right here. This goes back to the very simplest first things we learned. If you have a 2-carbon straight chain hydrocarbon, all single bonds, what is that? Robin wants to say it, I can tell. What is that? 2-carbon straight chain alkane. Methane. Someone.
Ethane.
Ethane. Okay, this is ethane. All right. So we are going to name this as, let me scoot that over. We have a methoxy group here. And then we have the same thing. We have a methoxy group here. I can shrink that down. Will let me? Okay. So it's going to be di-methoxyethane. Let me comfort you right now and say I'm not going to have a lot of questions for naming ethers on the exam. There may be one. Okay. But what you can see, if the only let me simplify this for you. If the only functional group in your compound is an ether, then you can name it as an ether. But if you have another kind of functional group, or if you have two ethers like this down here, then you name it a different way. You acknowledge the ether as a substituent, as a methoxy or an ethoxy or a propoxy group, okay? Questions on what we just did? Anybody so lost you don't even know what questions to ask?
So an ethane group doesn't have to be CH3, CH2, as long as it's two carbons, it always be an
Two
ethane.
carbons, single bonded.
Single bond, yeah, okay.
Okay. Properties for ethers, real quick. I'm gonna fly through these and you can go back and really study them, but we really need to move on. Ethers can engage in blank more or less hydrogen bonding than their alcohol equivalents. Remember, we said ethers cannot hydrogen bond with themselves, but alcohols can, so less hydrogen bonding. Alcohols can engage in more hydrogen bonding. So does that mean, and this is, I don't know why, it's like I accidentally repeated all this. Maybe one was supposed to be boiling point and melting point, but I just repeated the same thing, so mark out that second half. Ethers have higher or lower boiling points than alcohols of similar molecular weight. What do y'all think? We actually looked at an example of this on the very first slide number 3, I think. We looked at the different boiling points between like ethanol and then a similar weighted ether and an alkane. What do y'all think, higher or lower? Anybody remember?
Would it be lower?
Yes, it would. Because they cannot do as much hydrogen bonding. If alcohols can engage in more hydrogen bonding, they're gonna have higher melting and boiling points. Ethers are more or less soluble in water than similar sized alcohols. So we're just comparing them to alcohols. Alcohols are like some kind of carbon with an OH. This looks a whole lot more like water than this, right? So guess what? They are less soluble. Okay, I'm gonna skip over this anesthetic slide. You don't have to know anything off this slide. It was kind of just to make a point about the whole anesthetics thing. Okay, let's name these compounds. What was this? Additionally, ethers react readily with oxygen, therefore highly flammable. So they must be handled with care and stored in the absence of oxygen. Okay. Name the following compounds. So again, when you see things branched off like this, this is a methoxy group. And this is a methoxy group. So you're going to name it by looking at this central straight chain of carbons. So what is this? What is our parent compound here?
Prop
Yeah, a propane.
or propane, yeah.
So we'll write propane. And we got two methoxy groups. One is on carbon 1, one is on carbon 2. Whoops. So we'll call this 1,2 di methoxypropane. You'll see that 1, 2. So we're calling this carbon 1, carbon 2, carbon 3. Okay, on this next compound, here's what I see. The only functional group is one single ether. So we actually should be able to name this as an ether, like something, something ether, okay? So what we're gonna do is we're gonna name this group, and then put the word ether. Okay, just like what we did up here when we said methyl or ethyl methyl ether. But we have two different carbon groups this time. So what are these alkyl groups on the side? Well, what's the one on the left?
On the left, wouldn't it be methyl, and the right would be isopropyl?
Very close, Madison, but look even closer. There's 1, 2, 3, there's 4 carbons here. So this is a butyl group. And it's been a minute since we've looked at butyl substituents. Remember, you could have a butyl group, sec butyl, isobutyl, or tert butyl. So this, the one that we're attaching through, is bonded to 1, 2, 3 other carbons. So this is tert butyl. So this would be alphabetically, this would be methyl, tert butyl ether. Okay. Okay. So lastly, we have a methoxy group right here. We have a nitro group right here. And this right here is just plain old benzene. So how would y'all name this?
Would it be methoxynitrobenzene?
Yes, but we've got to indicate somehow with ortho, meta, or para, or some kind of numbering. Yes, Abby, para. Okay, these are spaced in a 1-4 grouping, and we got to name it alphabetically. M comes before N. So we can say 1-4, or you can say para, and then it will be methoxy, nitro, all one word, benzene.
How do we know that's benzene again?
How do I know what, Cameron?
That it's benzene.
That it's benzene? Because, so, let me scroll down, close your eyes, I don't make anyone dizzy. Okay, right here. So we said a benzene ring, and I drew this in yesterday on like this. We said that's benzene, okay? Now, we said there's some common names like this over here, toluene, phenol, and aniline, but we don't have any of these substituents on our benzene ring. So that's why I said it's just plain old benzene. Okay. Yeah, 6 carbons in a ring structure. It's an aromatic, nothing attached to it. That's just benzene. When you start adding attachments, you name them as substituents, or there's toluene, aniline, and phenol. Those are the 3 common names that I want you to know. It's in place of benzene. All right. I think that's it for naming stuff today. I want to go for about 10 more minutes, and then we're going to be done with lecture. Thiols and disulfides. So these are the last of the functional groups too, I believe. Well, we got carboxylic acids and stuff, but we're getting close to the end of the functional groups. Okay, thiols. Any compound, remember, that contains an SH group tagged onto it somewhere. Disulfide is any compound that contains an internal sulfur-sulfur bond, okay? This is internal, and this is always going to be terminal. It's going to occur at the end. So the way, well, I said we're done with naming, I lied. The parent hydrocarbon, you name that, and then you add the word thiol. So this one would be, this is ethane, thiol, And this is, let's see, we're gonna name this, and for ethane, we don't even have to put a number because no matter which carbon it's bound to, you get an identical compound. But here we do have to number it. So 1, 2, 3, 4. This is butane. So it would be 3-methyl, and then 1-thiol. 3-methyl, 1-butane-thiol. And the 1 here is indicating to us where the thiol group is attached, just like with alcohols. Okay, on a straight chain alcohol or a branch chain alcohol, you always got to put the number indicating where the OH group was attached. Same thing here, you got to put the number indicating where the thiol group is attached, just like alcohols. Now, sulfides, maybe you guys have heard this before. Sulfur tends to be a very, has a strong odor. Okay, so sulfides have really terrible odors, and that's oftentimes how compounds that have sulfur in it are recognized. So that's really the only property I think I'm going to talk about with the sulfides, is the fact that they have a really strong odor. Reactions of thiols and disulfides. So the way you can make a disulfide from thiols. So if you have 2 thiol molecules, the SH group attached on, remember the R just stands for some sort of alkyl carbon group, and then the SH group on another carbon, those can come together, okay? They're reduced, they lose their hydrogens, and you form a disulfide bond, okay? Notice it takes an oxidizing agent to do that. The oxidizing agent is what's reducing the 2 thiols. Remember, oxidation and reduction go together. If something's oxidized, something else is reduced. Thiols react with oxidizing agents to produce disulfides, what we just said. So here's an example. If you have methane thiol, so here's your methane and here's your thiol group. I have another one, methane thiol. They're just pointing backwards. Okay, if we have an oxidizing agent, we reduce those. All that's happening here is we're taking this hydrogen and this hydrogen, we're losing those, and then the 2 sulfurs are being bonded together. So you get dimethyl disulfide. All right. Don't worry about the fact that you also produce water. I would not ask you like what all the products are. On the flip side, so if you can use an oxidizing agent and make a disulfide, you can also take a disulfide, use a reducing agent, and break it back apart into 2 thiol molecules. So that is just, this is the opposite of this right up here. So you can take it out, it's just the reverse reaction. You can, disulfides regenerate your thiols upon treatment with reducing agents. Okay, so oxidizing a thiol yields a disulfide, and reducing a disulfide regenerates the thiols. Why is this important? This is actually really, really important when we get to proteins and enzymes. Y'all are familiar with amino acids, I'm sure. Whether you can name any amino acids or not is not necessarily important to me right now. But cysteine is a very important amino acid structurally for proteins. And right here, this yellow atom indicates a sulfur and a hydrogen. All the white spheres are hydrogens. Gray is carbon. Red, I think, is oxygen. But anyway, so we got a thiol group on our amino acid cysteine here. And this is amino acid, like I said, thiol side chain. It's important within protein structure and enzymatic reaction. So we'll come back to cysteine and disulfide bonds for sure. You will see disulfide bonds again. So based on what we just talked about, what disulfides would you obtain from oxidizing the following thiols? So if we have some sort of oxidizing agent and we have 2 of these, we're going to form a disulfide. Abby, I'm just seeing you had a question in the chat. Did I answer that a while back? I think I did. Okay. All right, so we would get CH3, CH2, CH2. Now here's the S. Now the H is going to go, and we're going to have an identical molecule bonded through its sulfur. So we're going to bond to the sulfur there and then just write the rest of the molecule. CH2, CH2, CH3, okay? And here is the disulfide. Skunk scent is next. So what disulfide would we get if we oxidize 3-methyl 1-butane thiol? Did we actually already, look, that is 3-methyl 1-butane thiol. We already have it. We don't have to think about how to draw it. So I'm not even gonna work smarter, not harder when you can. We would literally, you know what I'm gonna do? We would get this. I'm gonna erase this hydrogen by coloring it white. And that's what we get. So we get a bond to an S, and we just write the rest of the molecule in reverse. CH2, CH2, CH, boom, CH3, CH3. I literally just wrote the rest of this in reverse, okay? Right over here. You know what? It took me forever to figure out. Anybody ever been driving down the interstate before? And you like, wow, a skunk, you smell it in your car, it just hits you out of nowhere. You know what fixes it the fastest? It's not blasting your air on high. Roll down your windows and let it all out. I mean, it's gonna be miles behind you in a matter of seconds. Just roll down your windows and it goes away really quick. Why did nobody tell me that as a kid? Okay, halogen containing compounds. These are our last one, and then we got stereochemistry. Oh, we got 1 minute. We're not gonna finish in 1 minute. We're almost done though. Okay, alkyl halides. We said these are compounds that contain an alkyl group bonded to a halogen. Okay, so alkyl group could be methyl, ethyl, propyl, whatever. And it is bonded to like a chlorine or a bromine or a fluorine. Okay. These have been used in the past. Anybody heard of Agent Orange or 2,4-D? They literally used to spray this stuff out of airplanes over like in war times, like over like enemy territory. And it's terrible what it does. It just creates a ton of like, it can cause cancer, so many other things, but it's an alkyl halide because these chloride molecules right here bonded to your benzene ring. Another one, DDT, and these were also used as like pesticides and herbicides on food. And then they realized that's a really bad thing to do. So we now have much safer herbicides. Y'all probably heard of Roundup, okay? Notice within the molecule within Roundup is glyphosate. Thank goodness we don't use alkyl halides anymore in pesticides and herbicides. There's no halogen molecules anywhere in this molecule, okay? But we used to use really harmful stuff. So these are fortunately compounds of the past. But you got alkyl halides and aryl halides are when you have a compound containing an aromatic group bonded to a halogen. So this is actually 2,4-D is an aryl halide, okay, because you got the aromatic ring bonded to your halogens, okay? And so is DDT, that's an aryl halide. Okay, naming, same rules from naming alkanes apply here. But the halo substituent is then given as a prefix, as if it were an alkyl group. So, for example, number 1, we have a 3-carbon chain. This is propane. So it's just 1 chloropropane. The one telling us where the chlorine atom is bonded. Number 2, we got this bromine atom here. This is an alkyl halide, so this will be carbon. We got to start numbering near the end of the first branch point. So this is actually carbon 1, 2, 3, 4, 5, 6, because our first branch point that way is on carbon 2. So this would be 4, if we're going alphabetically, 4 bromo, and then 2 methyl, and then hexane. Okay, so this it should feel very much like naming alkanes. Okay. I'm gonna let you guys do these 3 and 4 as practice problems so that we can move on. The last topic of today, we got 2 slides left, I think, is stereochemistry. Stereochemistry is gonna become kind of a big deal from now on. And remember when I got you on the Blackboard course and I was kind of navigating you around the Blackboard course? If you go into the Blackboard course, there's a folder on there that says like extra stuff or extra info or something. There is a document in that folder that is going to be helpful for understanding stereochemistry. Okay, so if we get through these 2 slides and you're still lost on stereochemistry, download that and look at that today. Stereochemistry is what? It's the study of molecules that have the same overall connectivity of atoms but differ in their 3D arrangement. Okay, so they just have a different 3-dimensional arrangement, that's all. Stereoisomers, these are isomers with the same formulas. Atoms have the same connectivity, but again, different 3D arrangements. I'm just repeating myself. Within the umbrella of stereoisomers, you can have conformational isomers, okay? Because we can rotate carbon-carbon single bonds and we can make them line up or we can make them look different if we just rotate carbon-carbon bonds. Or remember, we can have cis-trans isomers. And we've actually already looked at what cis-trans isomers are. But both of these kinds of isomers are what we call stereoisomers. Okay. So to explain this concept really quickly, who here is right-handed? I'm right-handed. Raise your hand if you're right-handed. Are we all right-handed? Nobody's left-handed? Left-handed people? Okay, my husband's left-handed. I know a lot of left-handed people. Okay, nobody here is left-handed. But the point I want to make is that your hands are different if you're holding your hands up. Okay, if you hold them up like this, they are mirror images of one another, right? But if you lay them flat and overlay them, I can't get them to line up, right? Because they're oriented differently. Okay, your hands are mirror images and they cannot be, when we overlay something like this, we say we're superimposing it. So they cannot be superimposed over one another to get the exact same like shape. All right. So they cannot be superimposed in one another. If something is a mirror image, cannot be superimposed, we can also have this with molecules, and we're going to get into this deeper later, but we call these chiral molecules. If you have chemical molecules, compounds that are mirror images, and they cannot be superimposed, they can't line up if you lay them one over the other. We call these chiral molecules. Molecules that can be superimposed are chiral. So you have chiral and achiral. Okay. All right, I'm going to stop for today. I think we'll finish this tomorrow. We've done enough. I've done too much today. I probably should have stopped before stereochemistry.